When did we start? Oh, geez, 40 minutes. Sorry.
Is everyone here?
Well, yeah, everyone's here now. We just missed one page. Why is the double bond of an alkene rigid and unable to freely rotate? Are you nervous? It's okay. I do it all the time as well. We've got first our sp hybrid with the overlap of orbitals, and then the double bond means we have p orbital overlap. That p orbital overlap was the common gesture I was doing with the hands, okay, that we can't rotate because as soon as we rotate, we lose that alignment. So it's now just finding the answer choice that says that we can't rotate through our p orbitals. D. And since you're still looking at that page, do you have questions on that? I should have asked that first.
No,
You good?
I just wanted to make sure.
Okay.
Second
Can I get a picture? Sorry, I'm gonna get up in your face a little bit. Okay, no, that's not a little bit. That was aggressive. Ow. Correct name for the structure shown. I didn't look at enough people's work to see what was going on here, but just quickly scanning around both off of this one and a couple others, I would immediately say that what was happening is people were interpreting the drawing. The drawing is not a good place to start your interpretation. What you should do is actually start drawing it out. So carbon, then we have C2, there's 4 of them. So there's 1, 2, 3, 4. Then I have another carbon. Okay, my chain continues. 2 carbons. At that purple position, I have 1, 2, 3 carbons coming off. So there's 1, 2, oof. It's a little high up there. Can you guys see that?
Yeah.
Okay. So what's the correct name? What's the first thing we do?
Count the carbon chain belongs.
We identify the longest carbon chain. Guess what everybody identified as the longest carbon chain? Problem with that? There's a longer one. 1, 2, 3, 4, 5, 6, 7, 8, 9. Longest carbon chain. Remember, you have to go off axis. Okay? Particularly in a system that's trying to set you up in that scenario. You need to read off axis. There is no up, there is no down, there is no left, there is no right. Okay? So there's 2 of them that are non. So non being our 9 for 9 carbons. We have a 2 carbon chain off on the side, so it's an ethyl. Figuring out the number 1, 2, 3. It's at the 4th position because we want the lowest number. 4 ethyl non A and C. IUPAC for the following molecule. Numbering it was a good idea, which makes it easier for me. Assuming we numbered it right, yep. So we're looking at a hex. All of those are single bonds, so we're looking at a hexane. Okay, we've got a bromo. We've got a 2 bromo. Note numbering left to right gets us our smaller numbers. And we've got a dichloro, where the chloro's at position 4 and at 4. That's one you could argue potentially challenging. Why would you potentially challenge that and convince me otherwise? Okay. The rules do say you have to specify the location for every single substituent. At least one person in one of the exams, I don't remember which one. I think it was actually in the short answer, was saying that you wouldn't do 4, 4 because you've already specified it once. You have to specify every single one. So it is redundant, or appears to be redundant, but you're specifying the location for each of those chlorines. So it is 4, 4 dichloro. So your answer should come in as 2. There is the possibility of saying C because that has the same numbering. Why is C wrong? Alphabetic. Our substituents need to go in alphabetical order. B comes before C in the alphabet, so we're going to do 2-bromo. Line structure correctly named. Did you get that top one right? Oh, I can't tell. I would say good job on the numbering here. Finding the longest carbon chain is probably the relevant thing. So I'm going to guess, at least in this person's case, they didn't answer for 15, but they did answer for 17. With the structure, they were able to find the longest carbon chain correctly, which is nice, and may or may not have been able to find the longest carbon chain up there. Does that make sense? Can you kind of see that? Once you have the structure, it's a little bit easier to interpret, so drawing the structure can help. Right? With that, it's then trying to identify your locators, and they went through and numbered it both directions. So we're trying to look at our methyl. So if we go 1, the upper right hand to our first substituent would be at position 3. If we numbered it from the left, 1, 2, we get our first substituent at position 2, which means numbering it left to right is the better order. So we've got a methyl at 2, we've got a methyl at 3, a methyl at 3, and a methyl at 5. So 2, 3, 3, 5, which should be A. Make sense? For me personally, I would also, you're seeing me kind of do it with the dots, but I generally like to circle, particularly when I'm using a pencil, circle my main chain because that helps me identify it. In this case, after I've identified that main chain, since it's asking about the methyl groups, I would double back through and circle the methyl groups, knowing that I have to identify those pieces. So that's a work process that allows me to see what I'm trying to answer as quickly as possible. Make sense? Best name, we all struggle with dealing with how to draw bad things, 1, 2, 3, 4, 5, or interpret bad things. And this was one of the issues that I mentioned with nomenclature, is we can draw the structure from a bad name that doesn't make the name correct. Position 2, we have an alcohol. Position 2, we have a methyl. And at position 3, we have a methyl. Why is it a bad name? Step 1 of nomenclature is what?
Longest chain.
Where's the longest chain? 1, 2, 3, 4, 5, 6, 7. 7 carbons in your longest chain, not 6. Which means the root hex is wrong. Rank the following from lowest energy to highest energy. And I'll admit this one always makes me go cross-eyed as well. But what I'm going to try and do is the same thing that I would recommend you do, which is find your solid lines, which is what we did before. So note those solid lines are there, solid lines are here, solid lines are here. Everybody see that? Why is that helpful for me? Positions 1 and 3, those solid lines are in the exact same space, which means they are 1 and 3 are eclipsing. Because they are eclipsing, what does that mean?
Higher energy.
Which means 2 must be the lowest energy. And now it's deciding between 1 and 3. Okay? Looking at 1 and 3 now to differentiate between those, what I'm going to do is look for the non-hydrogen groups. So we're looking at a carbon, 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 and carbon. Okay? In structure 1, they're in the exact same space. They're eclipsing, whereas in 3, the carbons aren't eclipsing. Okay? What does that mean? 3 is lower, 1 is the highest. So 2, 3, 1, good process of elimination. Whether or not you got the right answer, you at least did a good process of elimination on what you could see within that. Okay? I would argue that for all of these, and this goes for all of the pages we've looked at, there was very little written down, and yet when I go through to do this, everything is written down. Is it easier to see the answer once it's written down? Write it down, right? The most common response I'll get to that, it takes too long for me to write stuff down. Then get faster at writing stuff down, right? It's not like I'm writing thought process. I'm drawing over the top of things that are already there, right? You need to pick up that speed and the fluidity with solving these things and writing that process down. As soon as you have it on paper, you will do significantly better, right? Last one, glucose, least stable. What are we looking at?
Whether they're axial or
It's an axial versus equatorial question. How do we decide stability? Which one's more stable, axial or equatorial? How do you spell axial? Not like that. Axial versus equatorial. Equatorial was more stable. So I want to find the one that's axial. How do I find axial?
look at the ones that are vertical.
Those are your straight up and downs. If we go through and take a look at A, are any of those going straight up and down? Okay. I would argue even looking at A, there might be some where you're like, I don't know, maybe. Like, is that going straight up? Is it different than the other answer? No, so it doesn't matter. Where's the only difference? Between those two spots, which one is going more straight up and down?
B.
B. That's the axial. What are we looking at here? This is cellulose versus the sugar glucose. Same general compound, all we've done is exchange the orientation of your OH. Questions about any of that? Yes?
What's the right answer on 15 again?
Sorry, on which one?
15.
15, 4-ethyl nonane. Can I get a picture? Cool, thank you. Whoops, went too far out. Achiral, of course, a challenging question. I did expect everybody just to get this one wrong, to be honest, just because chirality is challenging and we didn't spend a lot of time talking about it. What was our definition for chirality?
It has 4 different things attached to the carbon.
Okay, we're looking for 4 different things to a carbon, and that would then equal chiral. So what is achiral? Not that.
Yeah.
Okay, is really what it's going to come down to. So if we go through and take a look at structure 1, implied hydrogen, damn. With that implied hydrogen, what does that mean? There's now 4 different things connected to that position, which would make that, at least at first blush, chiral. Green was a horrible choice, color. So 1 is not correct. In 2, challenging to go through and look at it, but again, if we take a look at that spot, we've got 3 bonds out there and that 4th to a hydrogen. Do we have 4 distinguishable groups? Yep, which means chiral, not that answer. We go out and look at the last one, we've got hydrogens out here. So we could go through and put those hydrogens in, but it doesn't matter because that's only going to be 3 distinguishable groups because the double bond's going to the same space, which means structure 3 is the only one that is achiral. Answer choice C. Make sense? Okay. That's one where definition, had you memorized the definition, so I'm kind of on the fence on that one. If you had your notes where it said that's what it was, maybe that could have helped. You're still having to apply it, and that's where that challenge comes in. How many hydrogens on the following are in the following Lewis structure? Well, that's interesting. I think this one's there as a way to kind of draw hints backwards, because now we're explicitly asking about hydrogens, hoping that it sends up alarm flags being like, oh, we talked about this before. Or we've seen a similar question. So our hydrogens, hydrogen, 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 and then there's a line there. Should there be a hydrogen there?
No.
Nope, it already has 4 bonds. Dang. Okay, that's falling into the just kind of the rote spin around and just placing hydrogens, so you got to be a little bit more careful. So we get 1, 2, 3, 4, 5, 6, 7, and 8. Everybody got marked wrong on this because I couldn't remember the order that it was. So I just picked a random answer, and clearly I picked the wrong one. So that's one I did go back and add points to everybody for. Universally, you said more difficult, if you couldn't have guessed that already. Subatomic particle is most responsible for physical and chemical properties for an atom. It's the electrons. Consider that you're bringing 2 atoms near each other. The thing that interacts first is your electrons. The electrons are really going to dictate it. Protons do contribute. I think at least one person said protons, but it's the electrons that are first interacting, and it's how those electrons interact technically then to the protons, but it's that outer shell that's defining your reactivity. This is why when we look at Lewis structure, when we talk about electrons, we aren't talking about protons. Lowest energy conformation. Challenging one again. I think we're starting to move into the, oh my God, I need questions phase of the exam. And so I pulled this from the slides. As I said, you should go through and do this. Oops. So I want a cis-1,3 dimethyl cyclohexane, and it says lowest energy. Lowest energy was equatorial, so I would start putting it in as equatorial because the axial are straight up and down. Okay, I want the 1, 3, so that by definition is my position 1, 2, 3. I'm going to go to that third position. My axial is straight up and down, and there's my equatorial. Okay, that would be lowest energy. That puts them both aimed which direction? Down, which means cis. So that would work as an example. Problem with this is we now have to align that drawing with one of the answer choices. Okay, but I would argue it has been simplified by having drawn it out because we need to see them 2 equatorials aimed the same direction. It could be either up or down. So we look at A, those are straight up and down, so those are axial. B, there's an axial. C, that's 2 equatorials. That could be reasonable. D, dang, D is also 2 equatorials. How do I differentiate them?
The numbers.
Okay, couple ways to do it, which might be what you guys were both keying in on. This one's aimed down. That one's aimed up, which means
It's not cis.
trans, not cis.
Yeah,
Okay, so that would be wrong. Okay, the other thing that we could do, that position is 1. The very next position would be 2. What were we looking for? 1, 3. Answer C. Make sense? Any questions about any of that? Okay, did the wrong thing again. Can I get a picture of yours? Is this the last page? Well, I just need a picture so everybody can, so I can draw on stuff. Following rings is the highest energy. This was very much, I have no idea what questions to ask. We did talk about rings. We're talking about rings. Which one's the highest energy? Our 3-membered ring, we crank down on that angle strain, and that makes it the highest energy. Electronegativity of the element as you move right to left in the periodic table.
Oh
We
man,
go
I did not think about that.
right to left. Fluorine's the highest. We move right to left. Jiminy Christmas. Right to left, we're moving away from the fluorine. Since fluorine was the most, our electronegativity decreases. multiple answers before. I believe all three of these, you needed to select multiple answers. Select all atoms that should be labeled with an R or S. I said you didn't need to know how to label R and S, but you should be able to identify it because we use R and S to label what? Chiral atoms. So it's just asking where's your chiral atom. That's it. How do we know it's chiral?
There's 4 different things in it.
4 different things. So we now go through and look for atoms that have 4 different things. And in particular, we really only have to look at A, B, C, and D. Okay, so our A has that double bond, which immediately means, nope, not that one. B has 3 bonds, but there's an implied hydrogen. Would those 3 different things be distinguishable from each other?
Yes.
Yep, so B is a good one. C, again, has that implied hydrogen, which then means yes. D is showing wedges and dashes, which is really common for chiral molecules, except
2 hydrogens.
2 hydrogens. I can't tell a difference between them. It's not D. So it's only B and C. Okay. I believe with that one, in fact, it's not even believe, I know. If you just said B, you got half credit. If you just said C, you got half credit. Okay. But if you started selecting either A or D with any of those answer choices, I didn't give partial credit because you're undoing the work you've done. If you did B, C, and 1 wrong, I think I gave half credit. Okay. 29, following orbitals to use to make a sigma bond. Sigma bond, or what's the other bond? Pi bond. What orbitals do we use to make a pi bond? P orbitals. So what orbitals do we use to make a sigma bond? Anything with S. S is S, sp2 is S, sp3 is S. All 3 of those are correct. Okay, those are all involved in our sigma bond. So that goes back to the hybridization theory. Yes?
I don't understand the RNS. Or is RNS different?
Yes.
What is RNS?
R means the alignment of atoms around your chiral center match a particular configuration.
So what's next?
Means the configuration is the opposite of what R is. So what you're getting bogged down in is the how to define R and S. It's not what the question asked. The question asks, when do you do it?
Are you gonna learn that?
You did. When did you need to do? That's okay. It happened real fast. Really fast. When do we need to use R and S? When you have a chiral atom. That's it. That's all it is.
Well,
So,
we're gonna learn, like, this was-
how to do R and S? Yes, that's coming up. Yeah.
Okay.
That would theoretically be today, but I mean, 15 minutes is a bit rough, but we'll see. Polar covalent. How do we know we have a polar covalent bond?
When the electrons are unequally shared.
How do you know how they're shared?
Electronegativity.
What's the electronegativity for carbon?
Something. I don't know.
Oh, okay, so I don't like
It's
your
different
definition.
enough. It's different enough to know.
What are your types of bonds? Ionic. How do you know you have an ionic bond?
Metal, non-metal.
Really, the only important thing we need to see is a metal. Okay. How do we know we have a non-polar covalent bond?
It's the same as the
Same to same. That's the same to same. And C to H. How do you know you have a polar covalent bond?
Everything else.
It's not any of those. That's all it comes down to. So when we look at our answer choices, none of them are metals, so the ionic rule is out. Whoa. If we look at our non-polar covalent, it's same to same or carbon to hydrogen. Carbon to carbon is the same to same. Carbon to hydrogen is the same to same. Everything else, polar covalent. Questions?
Because hydrogen is an exception, right?
I don't know what you mean.
Like, I remember learning, like, it was the same atom, but hydrogen also counts even though it's not technically
So, and we'll push on this some more too. It is in the definitions that we walked through really early on in the semester. But when we're looking at those definitions, the same to same in carbon to hydrogen isn't the rule. Ionic being metal to nonmetal isn't a rule. They're guidelines. What's the rule? Which is where you were going, which was problematic. The actual difference in electronegativity. Okay? So the difference in electronegativity between carbon and hydrogen is small enough that we would classify it nonpolar covalent. Officially, I believe the line is less than 0.5 difference. That definition isn't useful if we don't know the numbers. That's why we memorize some things to help us through it. Okay? So same to same is the perfect sharing. Why do we bother to memorize carbon hydrogen and not any of the other multitude of potential cases? Carbon to hydrogen shows up everywhere. It's such a high frequency bond that we want to be able to classify it quickly. Make sense? So, if you look, as we went through and did this, you should have been seeing what work you had written down. Note for every single one of these, what did I do? Wrote down work, okay? So the argument that you don't have time to write things down is false, because we just did the whole exam writing things down, okay? And we had time to spare, okay? So any question you see, you should be writing something down. Get something down to prevent you from thinking within your head. Your head is a very scary, sketchy place to be. Don't take an exam in that space. Okay? I encourage you to come ask questions. I encourage you to talk to tutors about the exam. If you encounter any of my OChem students, they're like, oh, he lets you have the exam? Yeah, I'm letting you have the exam because I don't plan on teaching the class again, so it's okay for me to let it go and not worry about it. Okay? But ideally, it's not getting posted to the internet. You're using it as a study tool to improve how you can perform in the class. Make sense? Okay. With that, 115, right?
Yeah.
Okay. As I say, we're going to talk about it. I don't think I actually put it into the Unit 2 slides. I didn't. Damn it. Yeah.
Can I ask you to do more example?
One more example? Yeah. What of?
Can you draw 2 diagonal butane?
Yes. It's one of the short answers, right?
Yeah.
Nope, not there. Not there. Okay, bute, what does that mean? 4 carbons, they're all sp3 hybridized. At position 2, what do we have?
2 ethyl.
1, 2. 1, 2. Yeah? Okay. Something is wrong with the name. So this becomes one of the things we've got to be careful with. You're staring at the name being like, but I drew the structure. How could it possibly be wrong? Stop looking at the name. What's step 1? 1, 2, 3, 4, 5. What's wrong with the name? It's a pent, not a bute. Does that make sense? Is that all you needed out of it, presumably? Yeah. So yeah, officially it would be, what is that, 3 ethyl, 3 methyl pentane. Did I say 5? Yeah. We good? Okay. Chiral versus achiral. This is that handedness thing that we were talking about. Oh, of course. Right. And when we talked through it, we referenced the thalidomide being a problem. Okay? That squiggly line we said could be either a wedge or a dash. It's just not been defined. We're just really trying to call attention to it being important. So we could call it a wedge. There we go, it's a wedge. Okay? This would be one chiral form. Okay? It could have also been a dash. So really for this structure, there's two different forms for this molecule. Because there's two different forms, what am I going to want to do?
Draw them both.
We could draw them both. But if I'm going to communicate anything about this drug and I want to talk to someone about it, what might I do? Name it. So in that naming system, I would have to name that position was either wedged or dashed. So there were two options. What does that ultimately mean we lead to? R and S. Okay? That's defining the structure. So we would have to define the arrangement of those atoms around that spot. And ultimately it's saying, is that bond wedged or dashed? If it's wedged, we call it either R or S. I actually don't know because we'd actually have to assign it. Okay? But we have to follow a rule set that is consistent about whether it's R or S. Okay? We don't have that rule set yet. Okay? So we've got our classification scheme, which we've gone through before. Okay? Our stereoisomers, again, are hinging on finding asymmetry. And this is the big difference. This is where we're looking at our chiral centers, our chiral atoms. We're looking for an atom that has 4 different things bonded. That's our signifier. That's what we need. As soon as we've found that, we now have a chiral atom. Okay? That chiral atom can manifest to make the structure chiral. It does not have to. Okay? So, what do we end up doing, or what ends up happening both within lectures and in textbooks is they now go through and they say, well, look here, you see this asymmetry. Look here, you say this asymmetry. The problem with all of those arguments is that you have to adjust and change your viewpoint on the molecule to find the asymmetry. Is it drawn always so that you can see the asymmetry? No. Which means you have to be able to interpret multiple different drawings and different representations and get them into the interpretation that allows you to see what's going on. Okay? The easiest thing, and I'm not saying it's easy, I'm just saying it's the easiest of our list, is instead of looking for those kind of lines of asymmetry or planes or mirror planes or all of that, is to find an atom, typically carbon, with 4 distinguishable groups. Okay, and we keep saying distinguishable because even in the examples we've looked at, we've encountered multiple where there was 3 carbons, but could you tell a difference between those 3 carbons? What were they connected to? What were they connected to? And as long as you can differentiate those 4 different things, you have a chiral atom. Okay? How does that kind of manifest into our system? That's where we now start looking at classifying the relationship between different structures. Okay? So if you have this chiral atom or stereocenter or stereogenic, they're all slightly different definitions, and I kind of don't think it's worth troubling with. You can then classify your molecules according to these 3 new, categories. Enantiomers, or then diastereomers, or what's typically referenced as disastomers, okay? But it's diastereomer, just for the record, and then meso. Okay? Those 3 new classifications all come about because of chiral atoms. Okay? So you're responsible for being able to look at 2 molecules and say the relationship between them is that they're enantiomers. The relationship between them is that they are diastereomers. Okay? Why? A lot of it is proving that you can interpret the 3-dimensional model system. That's a lot of what exam 1 is about. What are the different viewpoints on molecules, and how do we interpret those viewpoints? Okay? So that's the intent of these. Since it looks like you are frantically trying to write something down, I'll leave that up there. Okay? But what I can do is bring up an example off the previous slide where we had something with the bromine on it. That drawing is inherently flawed. Okay? That drawing is problematic because it's showing 3 solid lines on an sp3 atom. That is false. That cannot exist. Okay? So what we're doing by drawing that is implying a bunch of information, or really implying that we don't care about the secondary information. Officially, we should be more precise, and we should say that that bromine is wedged, or that bromine is dashed. Okay? At first blush, we might say that those structures are identical. We don't need to worry. Why do we care? But this becomes the interesting part, is that those two structures are non-superimposable. If they were identical, they would superimpose. They don't. Okay? So we want to define that relationship. That's where we're getting into enantiomers. They're non-superimposable and they're mirror images. Do you see how they are mirror images? Some people are like, yes. Most people in the class, most sane people, those of you who said yes are just insane, okay, probably struggle to see the mirror image. So let's put a mirror there. Here's our new structure. See how it perfectly reflects through that mirror? Make sense? What is the relationship between this blue structure and this dashed one down here? Since you said that, we'll take that one. If we take this and try to superimpose, the backbone doesn't superimpose. But if I take this and turn it over, the backbone would now superimpose. Okay? But if I'm taking it and turning it over, what happens to that bromine? It's now at you, so it would be wedged. So this structure down here, our dashed bromine, is identical to this one. They do superimpose. Because the blue one that we drew up here is the mirror image of this one, I now know that these two are mirror images. I also know that they don't superimpose because our carbon backbone's aligned. So they are non-superimposable and mirror images. So what does that mean? I call these enantiomers of each other. You can't say, yes, you understand it, and then look like, no, you don't. You're killing me.
No, I get how they're mirror image. Wait, what is superimposable?
Superimposable means that you can move them into the same space. So if you made one a ghost, okay? So let's ghost this top one, and I want to try and overlap this into it. Put it into the space where that one is.
Could you draw one that would be superimposable? Can you do it?
You're not going to like it, but yeah, I'll do it. The purple one superimposes on the blue one. This one over here superimposes on the blue one. Okay? What does that mean? Superimposes means they're identical.
Okay.
All parts about them is that they're identical. So
If it's mirrored, it can't superimpose, right?
for them to be enantiomers, yes. Okay. Are these superimposable? Yes. Why? If I try to bring this over, right, there's that backbone, right? There's that backbone. This bond does not superimpose that bond. So why are you saying yes? You are 100% correct. These in the black box absolutely superimpose.
She can rotate that sigma.
Yes. The sigma bond is freely allowed to rotate. So that when I'm dealing with this whole superimposability issue, I have to be concerned about sigma bond rotations as well. Okay? So in black, they are superimposable. Are they also mirror images of each other?
They could be.
Yeah. They are mirror images. You're like, no, they aren't. They can't possibly be mirror images. If we take this and move it kind of up to the top, and we do that rotation, they are mirror images of each other. Okay? Which becomes one of the challenging things. You're like, oh, well, mirror images only happen in special cases. No. Put a mirror up and you have a mirror image. Anything can have a mirror image. The issue is the relationship between the mirror image and the partner, or the thing that generated it. Are they superimposable or are they non-superimposable? Okay? So it's not special that they're mirror images necessarily, it's that the relationship between them is that they are mirror images. Okay? Challenging? Abso-flippin'-lutely. Okay? But what you're trying to do is define those relationships. And where I think some of this struggle comes in is that you're trying to apply it on structures that aren't there, that examples that aren't there. So where we will pick up on Wednesday, that's the word, whoops, is two places. One, this guy. What we're going to do is draw all the possible wedge dash combinations that we can get out of this. Okay? If you've already got them drawn, it'll make Wednesday go a lot faster. And then what we'll do is look at the relationship between all of those four drawings and define them as enantiomers, mirror image, or we will talk about mirror images, but again, that's not a thing. Enantiomers, diastereomers, meso, identical, all of that. We'll define those relationships. Once we have those defined, that's ultimately getting us practice on classifying the relationships between those. Then we'll deal with the nomenclature part of it, which is our Kahn, Ingold, Prelog, dealing with R and S. And if you wanted to know how to do that, that's how you do it. What is R and S? When you look at the molecule from a very particular fashion, does it look clockwise or does it look counterclockwise? And if you're confused by that, that's because it's a very arbitrary system. Okay? It's been defined. You have to move it into that definition. If you don't know the definition, you can't answer the question. Make sense? Ish? That's not a question.